Section 3.3, Chemical Equations. A chemical reaction is described in the third hypothesis of Dalton's atomic theory, which is back in section 2.1, is the rearrangement of atoms in a sample of matter. Examples include the rusting of iron and the explosive combination of hydrogen and oxygen gases to produce water. A chemical equation uses chemical symbols to denote what occurs in a chemical reaction. We have seen how chemists represent elements and compounds using chemical symbols. Now we will look at how chemists represent chemical reactions using chemical equations. Interpreting and writing chemical equations. A chemical equation represents a chemical statement. When you encounter a chemical equation, you may find it useful to read it as though it were a sentence. Read: NH3 plus HCl, arrow, NH4Cl, as ammonia and hydrogen chloride react to produce ammonium chloride. Read CaCO3, arrow, CaO plus CO2, as calcium carbonate reacts to produce calcium oxide and carbon dioxide. Thus, the plus sign can be interpreted simply as the word and the arrows can be interpreted as the phrase reacts to produce. In addition to interpreting chemical equations, you must also be able to write chemical equations to represent reactions. For example, the equation for the process by which sulfur and oxygen react to produce sulfur dioxide is written as S plus O2, arrow SO2. Likewise, we write the equation for the reaction of sulfur trioxide and water to produce sulfuric acid as SO3 plus H2O, arrow H2SO4. Each chemical species that appears on the left of the arrow is called a reactant. Reactants are those substances that are consumed in the course of a chemical reaction. Each species that appears to the right of the arrow is called a product. Products are the substances that form during the course of the chemical reaction. Chemists usually indicate the physical states of reactants and products with italicized letters in parentheses following each species in the equation. Gases, liquids, and solids are labeled with G, L, and S respectively. Chemical species that are dissolved in water are said to be aqueous and are labeled AQ. The equation examples given previously can be written as NH3 gas plus HCl gas forms NH4Cl solid. CaCO3 solid yields CaO solid plus CO2 gas. S solid plus O2 gas yields SO2 gas. SO3 gas plus H2O liquid yields H2SO4 aqueous. Student note: students sometimes fear they will be asked to determine the products of an unfamiliar chemical reaction and will be unable to do so. In this chapter and in Chapter 4, you will learn how to deduce the products of several types of reactions. In some cases, the physical state must be expressed more specifically. Carbon, for example, exists in two different solid forms, diamond and graphite. Rather than simply write CS, we must specify the form of solid carbon by writing C diamond or C graphite. C graphite plus O2 gas yields CO2 gas. C diamond plus O2 gas yields CO2 gas. Some problems in later chapters can be solved only if the states of reactants and products are specified. It is a good idea to get in the habit now of including the physical states of reactants and products in the chemical equations that you write. Chemical equations are also used to represent physical processes. Sucrose, C12H22O11, dissolving in water, for example, is a physical process, section 1.2, that can be represented by the following chemical equation. C12H22O11 solid in water, H2O, yields C12H22O11 aqueous. The H2O over the arrow in the equation denotes the process of dissolving a substance in water. Although formulas or symbols often are omitted for simplicity, they can be written over the arrow in a chemical equation to indicate the conditions under which the reaction takes place. For example, in a chemical reaction, 2KClO3 solid yields triangle 2KCl solid plus 3O2 gas. The symbol triangle indicates that the addition of heat is necessary to make KClO3 react to form KCl and O2. So the symbol, the little triangle, delta, means that it's being heated, and heat is required for this reaction to take place. Balancing chemical equations. Based on what you have learned thus so far, the chemical equation for the explosive reaction of hydrogen gas with oxygen gas to form liquid water would be H2 gas plus O2 gas yields H2O liquid. This equation, as written, violates the law of conservation of mass, however, because 4 atoms, 2 hydrogen and 2 oxygen, react to produce only 3 atoms, 2 hydrogen and 1 oxygen. The equation must be balanced so that the same number of each kind of atom appear on both sides of the reaction arrow. Balancing is achieved by writing appropriate stoichiometric coefficients, often referred to simply as coefficients, to the left of the chemical formulas. In this case, we write the coefficient 2 to the left of both hydrogen, H2, and water, H2O. There are now 4 hydrogen atoms and 2 oxygens on each side of the arrow. When balancing a chemical equation, we can change only the coefficients that precede the chemical formulas, not the subscripts within the chemical formulas. Changing the subscripts would change the formulas for the species involved in the reaction. For example, changing the product from H2O to H2O2 would result in equal number of each kind of atom on both sides of the equation, but the equation we set out to balance represented the combination of hydrogen gas and oxygen gas to form water, not hydrogen peroxide. Additionally, we cannot add reactants or products to the chemical equation for the purposes of balancing it. To do so would result in an equation that represents the wrong reaction. The chemical equation must be made quantitatively correct without changing its qualitative chemical statement. Student note: when we study electrochemistry in detail, we will learn the method for balancing certain equations that does allow for the addition of H2O, H plus, and OH minus in section 19.1. Balancing a chemical equation requires something of a trial and error approach. You may find that you change the coefficient for a particular reactant or product only to have to change it again later in the process. In general, it will facilitate the balancing process if you do the following. 1. Change the coefficients of the compounds, e.g. CO2, before changing the coefficients of the elements, e.g. O2. 2. Treat polyatomic ions that appear on both sides of the equation, e.g. CO3 2-, as units, rather than counting their constituent atoms individually. 3. Count atoms and/or polyatomic ions carefully and track their numbers each time you change a coefficient. Combustion refers to burning in the presence of oxygen. Combustion of a hydrocarbon such as butane produces carbon dioxide and water. To balance the chemical equation for the combustion of butane, we first take an inventory of the numbers of each type of atom on each side of the arrow. C4H10 gas plus O2 gas yields CO2 gas plus H2O liquid. There's 4 carbons on the left side, 1 on the right. 10 hydrogens on the left side, 2 on the right. 2 oxygens on the left side, 3 on the right. Initially, there are 4 carbon atoms on the left, 1 on the right, 10 hydrogen atoms on the left and 2 on the right, and 2 oxygen atoms on the left and 3 on the right. As a first step, we will place the coefficient 4 in front of CO2 gas on the product side. Now there are 4. This changes the tally of atoms as shown. 4 carbons on both sides. 10 hydrogens on the left, 2 on the right. 2 oxygens on the left, 9 on the right. This changes the tally of atoms as shown. Thus, the equation is balanced for carbon, but not for hydrogen or oxygen. Next, we place a coefficient of 5 in front of H2O liquid on the product side and tally the atoms of both sides again. C4H10 gas plus O2 gas yields 4 CO2 gas plus 5 H2O liquid. There are now 4 carbons on each side, 10 hydrogens on each side. Now the number of oxygens is 2 on the left and 13 on the right. Note that the equation is balanced for carbon and hydrogen. Only oxygen remains to be balanced. There are 13 oxygen atoms on the product side of the equation, 8 in carbon dioxide molecules, and another 5 in water molecules. So we need 13 oxygen atoms on the reactant side. Because each oxygen molecule contains 2 oxygen atoms, we will have to place a coefficient of 13 halves in front of the O2 gas. C4H10 gas plus 13 halves O2 gas yields 4 CO2 gas plus 5 H2O liquid. There are now 4 carbons on both sides, 10 hydrogens on both sides, and 13 oxygens on both sides. With equal numbers of each kind of atom on both sides of the equation is now balanced. For now, however, you should practice balancing equations with the smallest possible whole number of coefficients. Multiplying each coefficient by 2 gives all whole numbers and a final balanced equation. 2C4H10 gas plus 13 O2 gas yields 8 CO2 gas plus 10 H2O liquid. There are now 8 carbons on both sides, 20 hydrogens on both sides, 26 oxygens on both sides. Student note, a balanced equation is in a sense a mathematical equality. We can multiply or divide through by any number and the equality will still be valid. Sample problem 3.3 lets you practice writing and balancing a chemical equation. I recommend that you retry this combustion reaction, the example that was given, on a separate piece of paper. Try it yourself. Do the carbon first, then the hydrogen, then the oxygen, then multiply by 2. Practice that one. Once you have completed practicing that problem, go to the sample problem 3.3. Try that one. Try this practice problem A. Try the practice problem B. Bringing life to chemistry, the stoichiometry of metabolism. The carbohydrates and fats that we eat are broken down into small molecules in the digestive system. Carbohydrates are broken down into simple sugars such as glucose, C6H12O6, and fats are broken down into fatty acids, carboxylic acids that contain hydrocarbon chains, and glycerol, C3H8O3. The small molecules produced in the digestion process are subsequently consumed by a series of complex biochemical reactions. Although the metabolism of simple sugars and fatty acids involves relatively complex processes, the results are essentially the same as that of combustion. That is, simple sugars and fatty acids react with oxygen to produce carbon dioxide, water, and energy. The balanced chemical equation for the metabolism of glucose is C6H12O6 aqueous plus 6O2 gas yields 6 CO2 gas plus 6 H2O liquid. Sample problem 3.4 shows how to balance and use the equation for metabolism. Try sample problem 3.4, practice problem A, practice problem B, do the checkpoints 3.3 chemical equations, 3.3.1, 3.3.2, 3.3.3, and if desired 3.3.4.